The momentum concept. It began from Newton's second law, and in its full form is written like that. Now, we are going to concentrate on what happens if my delta t is going to move to the left hand side. And then basically, I will do an integration of both ends. And you will know that integration means the product of two variables. That means it's the area under a force time graph. This area under a force time graph is equal to the change in this variable called momentum. And is defined as the sum of all the masses times a change in velocity, briefly the final velocity minus initial velocity. This equation is about that. The left hand side is called impulse. And the right hand side, okay, is change in momentum. Okay, Cedric? Rest. So, very often I give you a force time graph. What I mean is that if I have, let's say, a graph like that, this area under the FT graph, this is equals to the change in momentum df minus di depending on where your area is. Is that clear? So now I'm going to solve the first example for you, or rather you are going to do it. And I want you to refer to page 8 of your notes. And I'm talking about the dynamics notes, so all of you please turn over to page 8. I'm going to give you 2 minutes to look at it. Sorry? Okay, this kind of impulse, you will see that you have got changing force. This is not going to work if you are going to be just using N2L directly or N3L directly because you've got changing force. Your F equals to MA at the spot assumes that the force is constant. But because now my force is variational, that means it changes. Then later it changes and reduces. For this particular case, you have got no choice but to break the equation apart and take variation principle. Meaning to say you take integration, area and all that. So I taught you area under the graph is equal to change in momentum, half base height, and this area is equal to m df minus di. Your VI, VF first stage and second stage, I take the VF of the whole thing. I'm just breaking these two up so that you know that they are not the same. Okay? So VI and VF here. Here, after I calculate the area, half times base times height, I get 40 equals to mass. The final velocity here minus my start. My start velocity according to this scenario is 10 meters per second for this ball going through like that with gravitational force. So this is my initial speed. I plug in here, I get VF equals to 10 meters per second. Second. Now, opposite, let me know. So your V on A is actually, so if my force is opposite, I will take negative here. So we have negative 40, and you know from NFL, your electric size is 4, and FEA and my FAB are the same 30 meters per second for VF. Hence, this is the reason why part 2 I take the negative area. I still equate negative area because mass, this is called impulse. That means when there is a force nature on a very short force time at a certain time. Now, with this in mind, we will now practice short the rail, and this is how assignment I have for excited charge of your notes. Cedric, thank you very much. So now start opposite. So your V on A is actually here. This is your V on A. And you know from entry L of your year 3, for those of you who are year 4, FBA and FAB is the same. Hence, this is the reason why for part 2 I take the negative area. I still equate negative area equals mass times change in velocity. And that name is called impulse, force at a certain time. Now, with this in mind, you will now practice the real assignment I have for accelerated batch. Cedric, thank you very much. You will now start from here, goes to this point, and then ends up this point with final velocity Vf. But because it's a U shape, I want to break the parts into two. And hence, it's the easy part for me to break it at this point in the middle. People who are late, please don't walk in like a boss. Hurry up, sit down. Okay. Impulse is equal to change in momentum. So I've got the area under the graph equals change in momentum. So I take this first part, the area under the graph. Now, I expect all of you to know that your trapezium formula for area is half the parallel side sum A and B times the height h. You should know this Sec 3 formula. If you cannot remember, then you break it up into rectangle and triangle if you. But it's going to be very funny. Okay, I expect some form of decency for physics students. Your math should be quite good standard. So, using this formula for the first part of the graph, your trapezium area is half this 60 plus 80 times 25, and don't forget the axis is in the universe of milli. That's DCM, milli is 10 minus 3. So I cannot afford to forget that it's 25 times 10 minus 3. And that's the area on the left hand side, which is equated to change in momentum, mass times dF minus start speed u. My start speed u is 15. So this portion is 15 meters per second. And my job is to find what Vf1. And after I do that, you find that this is it. Now, you then find Vf1. After that, I equate that to here, my initial speed of 23.75. All the way to Vf2. This one is what I found finally, 30.8, but same thing. This area equals to m times change in velocity times m. Now, you realize I break up into two parts. I can also, in the next part, take this and this, take the area and take u and Vf. Actually, if you are careful, you should theoretically get the same answer. The reason why I take it out is because if this is a competition or if this is an exam, I purposely set forth a flag to check against my careless mistakes. No matter how smart you are, within a certain time, you are going to make careless mistakes. And I always tell my students, always check your answers, no matter how good you think you are, from 2 or 3 different directions. And your objective is to get the answer that you had obtained earlier. No point being fast if you are making like out of every 10 steps, 8 steps of careless mistake. You are as good as the person who knows 2 out of 10. No good. Okay? So please make sure you maintain your edge. Check. That's why I break it out into 2 separate parts, and I have to finish this as soon as I can. And generally, my students are taught for every paper you leave 30 minutes to 45 minutes as a double check. If not, no good. Okay? Thank you. There are 2 types of collision. Basically, completely elastic. That means I got 2 objects, one object hitting another, and the 2 of them move apart. It's like billiard ball. Point you go apart, point you go apart. That is completely elastic. Now, I want you to underline, for elastic collision, the momentum is conserved and the kinetic energy is conserved. That means I give you any scenario, the momentum before and the momentum after conserve one set of equation, KE before and KE after another set of equation. That is what it means by elastic collision. Any questions? Now next, I got inelastic collision. Now inelastic collision, the momentum is conserved, but the KE is not. That means for an object that goes like that, I got object A, object B, it goes like that, then they stick together. So when they stick together, it is inelastic collision. Stick together means completely inelastic. Okay? Now, next, I also want to teach you all something called explosion. The explosion is an inverted momentum problem. You will see that here, my momentum of a bomb exploded. All look up please. The momentum of a bomb like that, then later, boom. And all my little fragments go up. This is an inverted inelastic collision. So I picture and reverse the picture backwards. I got all the projectile outwards. They all go in, like let's say for example, I can reverse the camera. So all my camera will show this. All my particles go back and they begin to stick together. So your explosion is an inverted inelastic collision. Yes?
So how is momentum conserved?
I will show you a numerical example for that. So, continuing, going to page 2.
So,
Yes.
you can use momentum, the momentum equation to solve more questions. Then why would you need to know the KE?
That one, again, I need you to solve more questions, then you will know the relevance of the KE. Okay? Now, let's say I want you to now turn over to page 2 of your notes. Now, you will see that I have got first set of body and the second set of body. Draw them schematically. You always draw the after collision. When this guy knocks against this guy, you will draw it as N1, D1 pointing to the right, N2, D2 pointing to the right. You always draw this. Even if it goes to the left, that's not your problem. Let the mathematics sort it out. And then obviously I've got a start shown. So you always quote, momentum is always conserved whether elastic or inelastic. So I have to find the momentum before collision, which is the same as momentum after collision. So to do that, I take the mass times the starting speed. So I take m1 u1 plus m2 u2. This is your momentum before collision. That means I've got m1 hitting the other. I've got m1 u1, m2 u2, and then I product it and I sum it up. This is equal to momentum after, which is equal to m1 v1 plus m2 v2. And that's equation number 1. Now you realize that just to answer one of the earlier questions, why we need kinetic energy equation is because beside m1, m2, you realize you have got u1, u2, v1, v2, a set of u and v, two basic variables, and hence you need two equations in mathematics to solve. And hence you need the next equation, kinetic energy or somewhat. Understand, gentlemen? Now, here, inside this equation, given to you in a page 2, you realize that, okay, for this, I also have kinetic energy conservation. So, I will take this kinetic energy before collision, so half m1 u1 squared plus half m2 u2 squared, kinetic energy before collision, which is equal to kinetic energy after collision, half m1 u1 squared plus half m2 u2 squared. Now I want to say this. This is what is expected of you to equate both the momentum and KE. Now what is my problem? Anyone can point out? You realize that for the second equation, you have got the problem of square terms. So this method in mathematics, especially in physics, not so recommended. Mathematics you can go chong all the way for all, whatever. But in physics, it's not efficient. So we will normally use what we call the relative speed approach, which is given, the proof is given in page 2 in the middle, but I'll just give you the conclusion. So I'm now going to ignore the KT conservation method. I'm just going to use relative speed approach, and it's very simple. Now I want you all to pay attention now. The relative speed approach is this. You just need to alternate the method. So if I take U2 minus U1, my objective is to focus on the speed. U2 minus U1 from the back. So all I need is U2 minus U1. Since I started from the back, I can start from front here, I opposite it, equals to V1 minus V2. And I call this equation number 2. C is so much simpler. I can start from anywhere. I can take V2 minus V1 equals to U1 minus U2, and you still get the same answer. Any questions? Gentlemen, any questions for this? No question for this approach. We are now ready to do and try out some questions. Cedric? Thank you. So first and foremost, momentum before. I take this one times this one, mass times velocity, plus mass times velocity. But taking note, my convention is always right to the plus, hence this is negative 2. So these two constitute momentum before collision. Equated to momentum after collision, this is equal to m1 times v1, but your p1 is given to you as negative 3. So therefore this is 1 times minus 3 plus 2 times v2. So I only got one unknown in one equation. I can solve for v2. And wow. Any question for number 3? Now for number 4, and I will give you the edited number 5. Okay, our actual A-level question, I told you about that. You can have a good look at number 4 now and start doing. And take note, this is their MCQ question. Momentum apply, your kinetic energy doesn't. So I've got before and after collision. So m times 2v plus negative v times 2m, momentum before, equated to m plus m times the common speed v2. I equate this momentum before and momentum after, and you realize 0 equals to m plus n times v2. This is non-zero term. It therefore implies your v2 must be 0. If your v2 is 0, it means that your kinetic energy half mv squared is 0. Hence, both your momentum change as well as the KE is 0. The answer has to be A.